So lattice structure. So a lattice structure implies a partial ordering of elements, and that there is a top element and a bottom element. I'm not going to go too much into all the details of lattice theory here in this course. I did put some readings on the page if you want to see that. Very useful stuff, by the way. But most semantic structures are going to end up forming a lattice. And this is a good thing, because we can get some nice theoretical results from this that are important. And the ordering is just subset. And so it's really, at this point in mathematics, you don't have to prove that a power set forms lattice. This is just something that is so super well known. And you can see there's a top element with everything, a bottom element is the empty set, and that, the empty set is subset to all the singletons. Singletons are, each of them is subset to, a couple of the sets of two elements, and all of those are subset to the stuff above. So monotonic increasing in size, really easy to understand. So we'll get back to this in a moment, but just keep this structure in mind. So right now, you shouldn't be surprised to see a slide about let's restrict logic, okay? So, we started out with the classical propositional case, and right away, I showed you a couple of results that says, hey, we're already getting into NP hardness for things. That kind of sucks, right? But we can restrict it, and let's just make this kind of toy restriction. It's not particularly useful, so don't go saying that I'm teaching you that all logic is without negation is really great or fancy. It's not very helpful. But let's just say that, hey, we have only rules. Rules have a single atom in the head, and they have a conjunction of atoms in the body. No negation. When you take out negation, like everything gets very simple. But again, I'm using this as an educational, not that it's important for itself. So, okay. So, can we check? How can we check entailment? How can we go about doing that? And we can do this in polynomial time easily with the simple logic in a very structured manner using lattice theory and the fixed point operator. And the idea here is to help your intuitions along. So, as a great man asked me this morning, what is a fixed point operator? So given the logic program pi, T sub pi is a fixed point operator, and it's defined, it maps worlds to worlds or semantic structures to semantic structures. And our fixed point operator for this toy example, we're going to say T of W equals W union with the head of all rules such that the body of the rules is in W. All elements of the body of the rule is in W. Okay? So intuitively, what this means is I'm going to make one forward inference step based on the elements of W in that arc. Yes.
So yeah, we simplify this to like simple English. It's that everything that is satisfied, or like if the body is satisfied by the world, then like the head is in the set.
Yeah,
right?
exactly. So yeah, this function returns the world plus all the heads where that world satisfies the body of those rules. All right. So not really that complicated. I mean, maybe you're not used to the notation and stuff, how this is written, but when you think about it for a minute, it's actually pretty easy. Just one step of the inference process. And that's kind of the whole nice relationship between, lattice and fixed point theory and logic is, the inference process, can be equated to one application fixed point operator. And so actually, yeah, this is, I think, what we were just saying. So got an example. All right, so let's go back to our little universe here of A1, A2, A3. And here's the power set just for reference. And here's a simple logic program. We have a fact A. We have if A1, then A2, and if A2, then A3. And just show some examples. If we have the fixed point operator applied to A2, that gives us everything. Because A1 we get, we already have A2, and A2 implies A3, so we get that as well. But if we apply it to A3, we only get one in A1 and A3, because A1 was not in the original world, so A2 never gets concluded. This is only one step of the inference process.
Question.
Yeah.
So in the program, like one of the formula is a fact. So the head is A1, but there's no body. And that mean, we already know that A1 is a fact. Why do we have to put A1 where? All right, so we already have A1, right? And then A1 implies A2, or the rule is A1 as body, A2 as head. Why can't we just reason out A2 based on the blood program itself?
You cannot in this case, because what you're doing is you're checking all those rules and you're looking at just the body, each one that the world satisfies. So the world consisting of A3 does not satisfy this. We don't add it as we go along. The result, the output is different than the input. Yeah. Yes.
So the blue in the previous slide, that's the input.
The what in the pre?
So here.
Yep.
When we talk about that A3, what we were talking about, so we are unioning A3 with the set of heads from the program.
Yes. Yes. And that's kind of the key thing. And this is where, a single iteration is only concluding strictly that stuff.
All right, I have a question.
Sure.
So given a program pi, let t pi be a function that maps worlds to worlds. So if the program says itself that A1 is a fact, if I, use an empty set or empty brackets, imply a world with no atoms,
That only gives you A1.
oh, I have to iteratively do it again to have A2.
We will talk about that.
Okay.
That's multiple applications. This is a single application. So just like Jesse said, we have the empty set. Well, the empty set does satisfy the body of this third rule because that body is true. So true is fine, but everything else has an atom in the body. So the empty set does not satisfy that. Sure.
For the world in t by A3, the function t by A3,
Yeah.
we only have A1. And in the world pi, we also have A1 implies A2. So shouldn't
No, we don't. You only have A3. So A3 is a superset of the empty set. And A3 is not a superset of A1. And A3 is not a superset of this. So we only get A1. New added. Does that make sense? Other questions? Yeah.
just to confirm, so in T pi of A3, the reason we're not adding A2 as well, because A1 implies A2, that would be the next step or something like that.
Yeah, we'll get to that in a moment. You'll see. So as many of you have already hinted at, we can have multiple applications of this. And so now we put this superscript with I, which tells us how many times you apply this. So I'll say if I equals 1, and of course, some people might say this is the case where I equals 0, whatever. I use 1 because we know that's one application of it, just for this class. So I equals 1, you just have the fixed point operator. Any I greater than 1, you apply the fixed point operator to the result of t I minus 1. Okay? So and a fixed point is simply when the result doesn't change. So we know it's reached the fixed point at I when the result of I plus 1 is going to equal I. It can't change anymore. Now, let's look at a quick example. So here's our universe, here's our worlds, here's our program. All right. One application of the fixed point operator, as we saw, just give us A1. And here, I've even written out all the T's. It gives us A1 and A2 because we're applying it to here. And since A1 is a superset of A1, now we can conclude A2. So we got something else. And now we got A1 and A2. And now we get everything. And now we go to the fourth application and nothing changes. So it's obvious that if I do a fifth application, nothing will still change because, it's reached the fixed point. So what's nice about that is we can very easily show an argument that we can conclude all three of these starting with the empty set. Because the way this operator was written is you have to have a rule to conclude something. To add anything to that set in the output, there has to be a rule, which means everything in there, there's a series of rules that goes all the way back to the empty set. So it's explainable. We have the full line of reasoning as to why the system thought the way it did. One little note here, yeah.
Is it necessary that there will be a fixed point in any program?
We'll get to that. It's a great question. Will there necessarily be a fixed point? Oh. Yeah. But let's just talk about kind of correctness, okay? The correctness is usually the easier thing to show here because when you write the operator or when whoever's writing the paper wrote the operator, like they're thinking of this in mind. They're thinking of, let's have it look at the program and see what to do next. Now, one thing to note that's a little bit of a nuance here that you should have in the back of your mind is that this is going to come up with a line of reasoning, but it won't necessarily be the only line of reasoning that gets you that conclusion. Okay. And I'll leave it to you as an exercise if you want to work out, as to why. Okay, there you go. Happy now? Okay, so anytime we get some information about what elements, so this is what I was just saying. Each of these applications, we see that there was a rule that got us there, right? There we go. Okay. So the first thing is to kind of hit that point again on that the correctness, what we're actually getting out of here is we're getting what's called a minimal model, which means that anything that satisfies the logic program, any semantic structure is going to be higher on the lattice than where the fixed point operator ends up. So this is like the minimal things that we can conclude. Now, if we had, let's say, atom A4 in our universe, the world that has A1, A2, and A3, and the world that says A1, A2, A3, A4 would both be satisfying worlds. But A1, A2, A3 is the minimal model because it's the smallest possible thing. It's the most compact. Now, when you think of that minimal model idea, because it's a lattice structure and just everything above it is still going to be a satisfying world, this gives us a compact representation of the set of all worlds that will satisfy the program. So that's really cool because now we can answer our entailment problems. Okay, because we know everything that satisfies the program. So, okay, this is great. We solved entailment. But, I think I've given you enough verbal arguments where number 2 here, that the fixed point corresponds with the minimal model, makes a lot of sense. But how do we show that that fixed point exists? Well, remember a couple slides ago, I showed you the semantic structures created a lattice, yes. And so that wasn't just a fun mathematical fact, it's actually useful for some. So the Tarski-Master fixed point theorem states that any monotonic function over a complete lattice is guaranteed to have a fixed point. So what do we got to show? Well, we have to show that our semantic structure forms a lattice. So in this case, that was really easy. So then we have to show that the fixed point operator is monotonic. And in our case here, that was really easy too, because we're just adding things to that world. So of course it's monotonic. The result is going to either stay the same size as the input or get bigger. And so we can show that as well. There's one other practical thing about fixed point operators that's also important to note, is that in general you can show they converge in polynomial time. And the arguments will go like this. Think about the atoms we added. At each application of the fixed point operator, one of 2 things will happen. It either hits the fixed point or it's adding an additional atom. That's the only 2 things that can happen. And so, therefore, the number of applications can't exceed the number of atoms in the universe. It has to converge in that amount of time. Then you may say, well, what if you're dealing with fuzzy logic? Well, look at the number of bits it takes you to represent the number that you're assigning to the atoms. Multiply that by the number of atoms in the universe, that'll be the number of applications. So it's still polynomial in terms of the number of atoms you have out there. Okay? So this is a very powerful thing. And this will come up, getting back to NSR, this is kind of where sort of, separates the men from the boys and the women from the girls in terms of logic, right? How they deal with this problem. In things that use embeddings, they're kind of hoping that the embedding captures some of the chain of rules somehow, but they can't really describe it because they lose that information when it goes into the model. Inductive logic programming, most of that work will actually roll out the fixed point operator in the neural structure, but they can't roll it out to all n number of atoms. They actually put as a hyperparameter, we're going to roll it out k number of times. We're going to allow rule chaining up to 3. Okay, there's some problems with that, but some of that work they kind of have to do it because they run into big scalability issues.